Power relation in the AM wave. It has been shown that the component of the modulated carrier, that is the amplitude of the carrier, is unchanged. Energy added or subtracted, the modulated wave contains extra energy in the two sideband components. Therefore, the modulated wave contains more power than the carrier had before modulation takes place. Since the amplitude of the sideband depends on the modulation index, modulated voltage over the carrier voltage, it is anticipated that total power in the modulated be derived as the total power in modulation wave will be PT is equal to voltage carrier squared over the resistance plus voltage lower sidebands squared over the resistance plus voltage upper sideband squared over the resistance or times RMS, where all three voltage are RMS values in which the power is dissipated. The first term of equation 3-1 is the unmodulated carrier power, and PC is equal to voltage carrier squared over resistance is equal to voltage carrier over square root of 2 squared over R. So, ang magiging kalabasan, PC is equal to BC squared over 2R. Similarly, power lower sideband is equal to power upper sideband is equal to voltage sideband squared over R is equal to M voltage carrier over 2 over the square root of 2 squared divide R is equal to M squared voltage carrier squared over 8R equals M squared over 4 times voltage carrier squared over 2R. Substituting equation 3-12 and 3-13 into 3-11, we have total power is equal to voltage carrier squared over 2R plus M squared over 4 times voltage carrier squared over 2R plus M squared over 4 times voltage carrier squared over 2R is equal to power carrier plus M squared over 4 power carrier plus M squared over 4 power carrier. So, ang nangyari, power total over power carrier is equal to 1 plus M squared over 2. Equation 3-14 relates the total power in the amplitude modulated wave to the unmodulated carrier power. This is the equation which must be used to determine, among other quantities, the modulation index in instances now covered by equation 3-10 of the preceding section. The methods of doing this as well as solution to other problems will be shown in exercises to follow. It is interesting to note from equation 3-14 that the maximum power in the AM wave is power total is equal to 1.5 power carrier when M is equal to 1. This is important because it is the maximum power that relevant amplifiers must be capable of handling without. Let's have some example. A 400 watt carrier is modulated to a dip of 75%. Calculate the total power in modulated wave. Solution. Power total is equal to power carrier times 1 plus M squared over 2. Then substitute. Our power carrier is 400 times 1 plus ang M natin ay yung 75%, so i-decimal natin 0.75 squared over 2 is equal to 400 times the total of 1 plus 0.7 squared over 2. Then our total power is 512.5 watts. Then example 3-3, a broadcast radio transmitter radiates 100 at 10 kilowatts. When the modulation percentage is 60, how much is of this is carrier power? Ngayon, hinanap natin yung power carrier. Ngayon naman, ito yung formula natin. PC is equal to power total over 1 plus m squared over 2 is equal to 10. Substitute tayo. Ang ating power total ay 10 kilowatts over 1 plus percentage natin is 60 to decimal 0.6 squared over 2 is equal to 10 over the total of 1 plus 0.6 squared over 2 is equal to 8.47 kilowatts. Current calculation. The situation which very often arises in AM in that the modulated and the unmodulated currents are easily measurable, and it is then necessary to calculate the modulation index from them. This occurs when the antenna current of the transmitter is metered, and the problem may be resolved as follows. Let IC be the unmodulated current and IT the total or modulated current of an AM transmitter, both being RMS values. If R is the resistance in which these currents flow, then power total over power current is equal to modulated squared times resistance over unmodulated current squared times resistance is equal to modulated over unmodulated current squared is equals to 1 plus m squared over 2. Modulated over unmodulated current is equal to square root of 1 plus m squared over 2, or modulated is equal to unmodulated current square root of 1 plus m squared over 2. Modulation by several sine waves. Modulation of a carrier by several sine waves simultaneously is the rule rather than the exception. Accordingly, a way has to be found to calculate the resulting power conditions. The procedure consists of calculating the total modulation index and then substituting it into equation 3-14, from which the total power may be calculated as before. There are two methods of calculating the total modulation index. 1. Let B1, B2, B3, etc. be the simultaneous modulation voltages. Then the total modulating voltage will be equal to the square root of the sum of the squares of the individual voltage, that is, total modulating voltage is equal to square root of B1 squared plus B2 squared plus B3 squared plus and so on. Dividing both sides by voltage current, we get BT over BC is equal to B1 squared plus B2 squared plus B3 squared so on over BC is equal to square root of B1 squared over BC squared plus B2 squared over BC squared plus B3 squared over BC squared plus so on and so on. That is, MT is equal to square root of M1 squared plus M2 squared plus M3 squared plus so on and so on. Equation 3-14 may be written to emphasize that the total power in an AM wave consists of carrier power and sideband power. This yields power total is equal to power carrier times 1 plus m squared over 2 is equal to power carrier plus power carrier m squared over 2 is equal to PC plus power sideband, where power sideband is the total sideband power and given by power sideband is equal to power carrier m squared over 2. If the square root of both sides is now taken, equation 3-17 will once again to be the result. To calculate the total modulation index, take the square root of the squares of the individual modulation index. Generation of AM. There are two types of devices in which it may be necessary to generate amplitude modulation. The first of these, the AM transmitter, generates such high powers that its prime requirement in efficiency, so quite complex means of AM generation may be used. Here, AM is produced at such a low power level that simplicity is a more important requirement than efficiency. Although the methods of generating AM described here relates to both application emphasized will put on methods of generating high powers. Basic requirements comparison of level. In order to generate the AM wave of 3-4B, it is necessary merely to apply the series of current pulse in figure 3-4A to tuned circuit. At the oscillation will have an initial amplitude proportional to the size of current pulse and a decay rate dependent on the time constant of circuit, bearing in mind less 10 times as many pulses per audio cycle. Feed to a practical circuit that result extremely good approximation of an AM wave will result in the original pulse are made proportional to the modulating voltage. This process is called flywheel effect and it works best with tuned circuit whose Q is not too low. It is possible to make the output current of a Class C amplifier proportional to the modulating voltage by applying this voltage in series with any of DC supply voltages for the amplifier. Accordingly, cathode, grid, and anode modulation of Class C amplifiers are possible. In AM transmitter, amplitude modulation can be generated at any point after radio frequency sources. If the output stage in transmitter is plate modulated, the system is called high modulation. If modulation is amplified at any other point including some other electrode of the point amplifier, then so-called low-level modulation was produced. Makikita nyo sa figure 3-5 AM transmitter block diagram. It is not feasible to use plate modulation of the output stage in the television transmitter because of difficulty in generating high video powers at the large bandwidth required. Grid modulation of the output stage is the highest level of modulating employed in TV transmitter. It is called high-level modulation in TV broadcasting, and anything else is then called low-level modulation. There are a lot common features. Both have a stable RF source and buffer amplifiers followed by RF follow amplifiers. In both modulation, system audio and power audio frequency AF amplifier are present, culminating in the modulator amplifier, which is higher power audio amplifier. To exaggerate the difference, an amplifier is shown where follow the modulation RF amplifier for low-level modulation and seen that it must be an linear RF amplifier. Each of the system is seen to have one great advantage: low modulating power requirements in one case, and much more efficient RF amplification with simpler circuit design in other. It has been found. At sa figure 3-16, makikita nyo ang grid modulation class C amplifier. In practice that, a plate modulated class C amplifier tends to have better efficiency, lower distortion, and power handling capabilities than a plate modulated class C amplifier. The plate modulated class C amplifier is the standard and most widely used method of obtaining amplitude modulation for broadcasting and other high power transmission application. The audio voltage is placed in series with the plate supply voltage of a class C amplifier. Most frequency modulated in this manner is the final power amplifier of the transmitter. The output of the modulating amplifier is normally applied to the PA through an audio output transformer. This system is sometimes called anode B modulation. Anode modulation of output power amplifier and class B operation of the modulator, the latter having transformer output. Transformer permits the use of class B modulator, giving good audio efficiency. It also allows 100% modulation to be achieved, since the output of the modulator can be stepped up to any value required. As a result of these considerations, this modulation system is employed in a vast majority or AM broadcasting transmitter. At ito yung example na circuit. Transformer modulation using triode. The equivalent circuit of figure 3-8 has been transformed output neutralized. It also shown as it was for a grid modulation amplifier. Since it will certainly be necessary to avoid the Miller effect in triode at high frequencies, a shunt-fed C amplifier is shown mainly to simply the explanation. It may or may not be used in practice. Note that a coke is placed in series with the modulation transformer to protect it from RF damage. It is seen that the same supply voltage, VVV, is used for both the PA and the modulator. This means that the peak modulator output voltage is made less than VVV to avoid distortion. A value of VAF is equal to 0.7 VVV is optimum. Since the peak-to-peak modulator primary voltage is 1.47 VV and an audio voltage equal to VVV is required to produce full modulation, the transformer turns ratio in this case will be 1.4:1. Although fixed bias supply BCC is shown in figure 3.9, this fact result is better operation. The first waveform of 3-10 show total plate voltage applied to class C amplifier, and the second show resulting plate current. This is seen to be a series of pulse government by the size of modulating voltage, and when these are applied to the tank circuit, the modulated wave of the waveform 3-10